Okay, so let me illustrate what is shear force in bending moment diagram before I throw on you math, which uh, which is sort of straightforward here. But what exactly is shear force in bending moment diagram in context of beams? So imagine that there's a simply supported beam. Here, a simply supported beam is actually a concept where you have the supports as shown, and then there's a force P acting midway. That's a simply supported beam. Okay, and the first step is to draw a free body diagram, which we've seen. And in this case, well, there is VA, VB. I should just mention that this is L divided by 2, L divided by 2, HA. And so it's not hard to see that HA is 0 because there's no horizontal force. Since the force P is exactly midway, you should get VA equals VB equals P divided by 2. Okay, so far so good. We've done this. We've talked about how to compute those. Here you can just do it by inspection. Okay, now let's come to shear force and bending moment. Okay, now what if I actually take this and just cut it here, chop it off? So if I take the beam and I cut it off, so you think of a free body diagram of a free body diagram. Here we have a beam, we chop it off, and now we want to compute the reaction forces because we are trying to, of course, draw a free body diagram of the individual parts. So if you have this set up, then clearly you would have not one but two free body diagrams, one for each of those two beams. Think of that like a think of the think of this as like glue, which is holding them together. Think of that, the way this setup is almost like a fixed support, right? It's glued to the wall. Similarly, it's glued to each other. And we can write similar forces as that of a fixed support. There would be a force V, right? For this one, we had what? We had a vertical force, a horizontal force, and a moment. Okay, so we'll have vertical force, we'll have a horizontal force, but since the beam as a whole doesn't have any horizontal force, H would be 0. So we're left with only two forces, V and M. M. Now, if V and M is as shown on the left side, it has to have an equal and opposite reaction on the other one. So we'll have V on the right and M on the right. Okay, so that comes from our reasoning for a fixed support. It's exactly like a fixed support with H equals 0. Okay, now we do the reverse. We have actually cut it up. We can actually glue it together. You should draw it like this. So now if you take the beam and you glue it together, okay, this glue has to basically overcome V and M. It has to basically keep it connected, keep it joined. It has to be able to sustain a moment M and a shear force V. Okay, and that's basically where the beam is going to be the weakest because we cut it, and the glue is probably going to have its own issues holding the thing together compared to something which is solid metal or some other material, right? So that's the weakest link. And when we typically design things, we will see that we join things together. Those tend to be the weakest sections because those sections have to bear moments or forces and so on. Okay, so the shear force is something which appears, and the bending moment appears in the beam as we sort of chop it off and look at it with our tools we've developed so far, reaction forces. Sorry, free body diagram and reaction forces. So in this section, what we're going to do is, so this section, we are going to compute V and M for a beam. So this V and M I've shown you for one section, but you can do it for many chops all along the section, and you can find V and M. You'll see that V and M changes as you go along the beam. Okay, and V and M is going to be important because that V and M, the shear force and bending moment, are actually related to the stresses. So next section, will be connecting V and M with stress. And there's another stress which we've not talked about, is shear stress. Shear stress, stress. Okay, and why we want to get to these stresses, because when we design something, we want to use the stresses as a criteria for design. For example, we've talked about ultimate strength, yield strength. Those strengths are connected to the diameter and cross section and so on. And so that's the way we link stress with design through that curve I showed a little bit a while back. Okay, so let's compute V and M, and then later on we'll connect V and M to stress and strain. So we look at beams because many of the mechanical objects we'll be analyzing in this course can be analyzed by thinking of them as beams. So here is sort of a refresher. You've probably done this. We'll talk about the types of forces. Okay, we can have a beam with a force P, Newton. This P is called as a concentrated load. Okay, another type of load is what is known as a distributed load. It will be shown this way. Okay, I'll use W, but this is basically Newton per meter because it's spread over a certain length. So this is an example of a distributed load. We could also have a moment. The units are Newton meter. Okay, so just like previously we talked about drawing free body diagrams, this is just showing you the different types of loads that can be applied. All you do is use these loads to factor these loads in order to do the free body diagrams and then compute the reaction forces. Okay, here are some formulas. I won't get to the derivation, but they have probably been covered before in a course, maybe in statics. Q is load intensity. V is shear force. M is bending moment. Then the following is true. Okay, the way you derive this is basically you draw a free body diagram for a small section of the beam, then you see how the moment changes for that small cross section, and then you do equilibrium about the x and y direction to get these equations. So V is dm dx, Q is dv dx, But if you put v equals dm dx, you can write d square m dx square. So this follows from using v equals dm dx. So the shear force is the rate of change of moment. The load intensity is the rate of change of force, or the second derivative of the moment. Okay, now you could integrate this equation to get, so that'll be dm equals v dx. You could integrate this from, let's say there's two sections of the beam, A and B. So left hand side, we have mb minus ma is integral ba v dx. Okay, you need to sub in the values for v in order to compute what that mb minus ma is. This basically tells you the rate of change. It basically gives you the moment between points A and B, and we'll actually use this in some problems. Okay, so I just write those down. So then you can also do the same thing here. We can write Pb minus Va equals integral q dx A to B. Moment diagram. This literally means that we'll be drawing V as a function of x and m is a function of x. Okay, x being the length of the beam. Okay, how do you get this to this point? Well, first, I'll just be putting together what we did before, draw a free body diagram. We've done that. Assign a coordinate frame, something we've already done. Next, we'll compute the reaction forces. We again did this in a problem. Compute the reaction forces. This is done by summing forces. Okay, now the fourth step is the step which is compute the shear force. Bending moment. Okay, and this we need to do at every location of the beam. Using these equations. P equals dm dx, I wrote them down earlier, and Q equals dv dx. So what makes it probably a little harder is that we need to do it at every location of the beam. There are some shortcuts which we'll see, but in general, you need to do it at every location. Okay, so the sign convention. So I have a sign convention for the coordinate frames. This is for the reaction forces, but I need a sign convention for V and M. So the sign convention we'll follow is this. As I said, we'll break the beam down into a left section and right section. On the left section, we'll assume that for the moment, counterclockwise is positive. On the right section, clockwise is positive. For the shear force, on the left side of the beam, V downwards is positive, and the right side, V upwards, is positive. So this, by the way, is I have cut the beam. So when we'll do this analysis, we'll see that there are two ways to go about it. You can start from the left and keep moving to the right, or you can start from the right and keep moving to the left. Okay, I'll stop here. I'll do a problem next time on the shear force bending moment diagram. We'll meet on Tuesday. Monday is a holiday, but we'll meet on Tuesday, and there's a homework due. If you need more time, let me know, since it's a holiday.